Hello, this is Calculus 1, Lecture 13A, Part 1, Antiderivatives. My name is Scott Grizzard from the University of South Florida. If you are in the class, just to remind you, these two-part lectures, you will need to watch Part 2, which is on the min-max function as well. So they're both part of Lecture 13A. So what we want to talk about today with this lecture video is initial value problems, antiderivatives, and so on. So we've been taking derivatives, now we want to go backwards. So here's a typical problem. Let's let f prime of x equal 30x squared. Now, can we go backwards? Yes and no. We can go backwards if we have a little bit more information. So what functions have the derivative 30x squared? Okay, so let's look at some examples. Okay, let's say g of x, this function, if I take its derivative, is 30x squared. So it is a function whose derivative is what I want. But let's look at another function. So here are two functions whose derivatives are exactly the same. Both derivatives are f. So can I find just one f? Well, if you recall, these functions almost differ by a constant. That's one of the things we proved using the mean value theorem. Right? Any function of that form where c is some constant will have the derivative of f. And what I need is the specific one, right? And I know this because I know f of 1 equals 10. So what I'm going to do is I'm going to plug that in as well. So so the particular f that I'm looking for is going to equal 10 when x equals 1. So in this particular case, f is simply 10x cubed. So here are the three big ideas. There are an infinite number of functions whose derivative is f. All of these, we'll call them antiderivatives. They differ by a constant. So again, I had g of x equals 10x cubed plus 0. H of x equals 10x cubed plus 50. All of these have the same derivative, right? Because they differ by a constant. A constant, when I take its derivative, is just 0. So there are an infinite number of functions whose derivative is f. All of these antiderivatives will differ by a constant. And if I want the specific, right, if I want the specific function, I'm going to need a little bit more information so that I can solve for that constant. In this case, what I needed was the place where f of 1 equaled 10. Okay, so those are my big ideas. Okay, here's a similar problem, but now I've got the double derivative, and I've got some initial value information, and what I want is f of x. So, here I've got f double prime. I need to go up twice. Okay, so the first thing I need to do is take the general antiderivative of that piece. Okay, so what I did was I undid the power rule by going up 1 and then multiplying by a quarter. Okay, and now I need to solve for c. Okay, so I get my c of 1, and now I'm just going to put that back into this equation. Okay, well, I only have f prime. What I want is f, and I've got an initial value also for f. So I can go one more. And I'll call my new constant that I'm solving for d, just so I don't confuse it with that c. And then I have the 39 over 10, which was my constant, so that I just add those up, and that's my f. So I took the general antiderivative, I undid the derivative for this piece first, and I got that with some c that I then solved for. Then I undid this, the derivative here, and I got that, and then I solved for the constant again, which in this case was D, and then I put it all together. Okay, so let's look at one of these as a word problem. Alan Rickman, if you've ever seen the movie Die Hard, which is a Christmas movie, I am taking a political stance on that. Alan Rickman is dropped by Bruce Willis off the 35th floor of Nakatomi Plaza, which is about 630 feet. Now, acceleration due to gravity is 32.2 feet per second squared. So my question is, how long does it take for Alan Rickman to go splat? So, what do we have for his initial values? Well, we know his initial height is 630 feet, and we know that his initial velocity is 0 feet, right? He's dropped. He's not pushed or shoved or, he doesn't have any initial velocity. He's just dropped. So now, and remember that the derivative of height, in this case, would be velocity, and the derivative of velocity would be that acceleration. So what I have is the exact same problem I had before, except with words. So what I need to do is I need to take the antiderivative of acceleration. Now, I've marked this A with a -1 in the corner here. I'll get to that notation in a minute. But this is one way of denoting the antiderivative. So the antiderivative of acceleration is -32.2 t plus some c. Well, since his initial velocity was 0, okay, I know that 0 is going to equal -32.2 times 0 plus the c. That gives me the c of 0. So that gives me a nice, easy velocity formula to work at. We like that. Now I need to take the antiderivative again in order to solve for his height. So I do that again, and I'm going to wind up solving this. It's going to wind up being -16.1 t squared plus 630 after I solve for the constant, the d equaled 630. So now I want to know how long it takes for Alan Rickman to go splat. In other words, what I need to do is find out, when his height equals 0. So, right, because that's when he hits the concrete. So if his height equals 0, I'm going to plug that into my height equation, and I wind up with 630 equals 16.1 t squared. Okay, so I divide and I take a square root, and I wind up with something like 6.2554 seconds. So Alan Rickman is going to go splat in approximately 6.2554 seconds. Of course, I also have a negative root, but, I don't care because you can't have negative time. Right? This is Die Hard, not Back to the Future. Okay, so that's how I would solve one of these kind of word problem. So let's put some of this together. Let's give some definitions. An antiderivative is just some function whose derivative is the function I'm after, right? So if I want an antiderivative for f, g would be an antiderivative if g prime of x equals f of x. So example, if I have f of x equals 3x, then g of x equals x cubed would work, right? But so would x cubed plus 6, right? So I've already talked about the fact that I'm going to have an infinite number of functions, all differing by a constant, whose derivative is the function I'm looking for. So what we call the general antiderivative is that f is the collection, the general antiderivative is going to be the collection of all functions whose derivative is f. And we're going to denote that with this -1 bit for the moment. So we've got f to the -1. And the book likes this big capital F. I don't like that because it can be confusing. This is unambiguous, although some people confuse it to the inverse notation. It's not an inverse, it's an antiderivative, right? So f prime is the derivative. After I get past the second, remember that I'm going to start doing this kind of third business here. So the idea is, okay, if I'm going to denote f to the 3 in parentheses, which is different than f cubed, as the third derivative, Well, why don't I just stick -1 in the parentheses? So if I want to go up instead of going down, I'm just going to put a negative there. So I've got the first antiderivative. And then I've got a second antiderivative. And notice, though, that each of these are not a function. They're a collection of functions. Okay. So what I'm generally going to write is I'm going to put some plus c at the end of it. So I'm going to take some antiderivative, right? And I'm going to let it be plus c. Okay. So if f of x equals 3x squared, f to the -1 of x, the general antiderivative is going to be x cubed plus c. And again, there's another notation for this, which we're going to get to, kind of like AUC. This is not the most prevalent notation, but it's the best one for what we're doing for. Now, this is actually in common use. The AUC notation is only for the area under the curve, is only still used basically in medical school, pharmacokinetics. This is a little bit more general. So I'm doing something that's not perfectly standard for the moment, but it's not out in right field either. And we'll get to why I'm doing this later and what the more general notation is. Okay, so let's turn our attention to 1 over x. 1 over x, recall that the derivative of the natural log is 1 over x. But x here has to be greater than 0. If x is less than 0, then log of x is not defined, because log of x is only defined for the positive numbers. However, log of negative x, right? So -1 times x. If x is negative, that's going to be a positive number. So if I multiply the negative number by -1, I wind up with a positive number, and then I wind up with somewhere where I could take the derivative of the natural log, because now I'm positive. Natural log is defined. So again, x is less than 0. I multiply it by -1. Now I get a number that's greater than 0. I could take the log of something greater than 0. I'm going to do the chain. I'm going to get a 1 over u times the derivative with respect to x of -x. So I get 1 over -x, right? That's the derivative of the outside times the derivative of the inside, which is the -1. Well, -1 times 1 over -x is simply 1 over x. So the book is going to do the following. The book is going to say, okay, since the derivative with respect to x of the natural log of absolute value of x equals 1 over x, for any x that's not equal 0, it's going to say that the general antiderivative is of natural log is log of x plus c. The log of the absolute value of x plus c. That's okay, except that there's this landmine. And the landmine is the fundamental theorem of calculus. Okay? And the fact that you can't cross 0. All right? So hold on to that thought for just a moment. I'm going to talk about this thought for just a moment, about why I don't like this. But it is common, so we're going to go with it. But I'm just going to say that there's this landmine that they're inviting you to step on. And we're going to talk about that landmine in a moment. Okay, another aside is that not every function has a pretty antiderivative. So we had nice and pretty derivatives for just about everything. Antiderivatives don't work like that. Okay. Well, let's look at the fundamental theorem of calculus, and then we'll talk about this landmine. Okay. So let D be, we had this last time, let D be an interval, A some base point in D, and F defined on D. If F is continuous on D, and G is some function, so that G prime of X equals F of X, then these two things are true. Well, notice something in here. G is some function, so that G prime of X equals F of X. In other words, G is an antiderivative of F. What's more, if the derivative of AUC FA of X equals F of X, that means that AUC FA of X is an antiderivative for F. So there are two interesting things in here in the fundamental theorem of calculus. Also notice that D must be an interval. Now, let's go back to our antiderivative definition and why I didn't want to talk about this one over, why I wanted you to watch out for a landmine. if f of x equals 1 over x, right, then AUC f to the negative 1 of 1 is not defined. I can't use the fundamental theorem of calculus on this because log of x, a log of 0, is not defined. So I can't cross 0 with the fundamental theorem of calculus. So this is the landmine that the book is inviting you to step on, and I just want you to be aware of it. Okay, and that will make, we'll talk about that more later. All right, there's another way to think of Alan Rickman here. If the velocity of t equals negative 32.2 t, I can think of this as the time it takes, the antiderivative here. Instead of solving it like an antiderivative problem, I can also think of it as an area under the curve problem. I want to know the area under the curve of the velocity function. I want to find when, for what x, will that equal negative 630. I want to find that number. And that number, if I do AUC V0 of 6.2554, I'm going to find that that's going to be negative 630 if I take the area under the curve up to that point from 0. So even if I don't have a clean antiderivative, I can get at these things by using an AUC. And here's this idea that this is actually another antiderivative. And if I could find the A, that's where my initial value comes in. And we're going to talk more about this later. So this is just kind of a little preview. Okay. All right, so I have this idea that area under the curve and antiderivatives are related. They're related through the fundamental theorem of calculus in multiple places. And so what I want to do is I want to get at these antiderivatives. I want to firm this up because what we want to do ultimately is prove the fundamental theorem of calculus. And so next time in lecture 13b, not in the part 2 here, we're going to actually talk about that when we talk about Riemann sums. But in order to talk about Riemann sums and prove things with them, we need to talk about the min-max function. And that is part 2 of this lecture 13a. So join me for that one, the part 2 of 13a, the min and maxes function, and I'll see you in a moment.